Hello and welcome everyone to Process Dynamics and Controls Homework 4 Part A. And in today's video we have a couple things to go over. The first Part A will be 4 parts, and the first part of this is going to begin with us assuming that the viscous damping in a manometer can be expressed in terms of the pressure drop associated with laminar flow. And then we will derive the transfer function relating the height difference between the fluid levels in a manometer to the pressure differential. We will then, for a water-filled manometer where the total length of the fluid is 1 meter with a tube diameter of a centimeter, determine the gain, damping coefficient, and time constant of that second order system. And then we will simulate this response to a 50 PA step change in pressure. And then two things left, we will show algebraically the first two order systems in series. And then we will also computationally simulate the behavior of the second order equation in Colab. So without further ado, let's begin. So the first thing that I'm going to do here is draw a diagram of our system. And so it's going to look like a U. So let's draw it better. So we have our system here, and then we will have a liquid level here, and the height it needs to raise we will label it as such. So we need to first create an equation for this, in which we will call this the force balance. And to do this, we're going to set our force is equal to our gravity plus our atmospheric pressure plus our viscous forces. Once we put those in actual variable terms, you get force equals negative gravity times density times area times height plus pressure atmosphere. So now we also have to break down this equation here. So we're going to bring this down, and you get an equation, delta P over rho is equal to our mu value times F over length divided by diameter multiplied by our velocity average squared over 2. Now we can break that down even more, down to delta P over rho equals, plug in our values from the specifications, 32 length v squared average times mu over d rho v d. And now you can cancel out these rows, sorry, my allergies. And you can get the equation even more down to area times delta P is equal to 32 length v squared avg mu over d squared all multiplied by area. And then the final step in the equation is P viscous times A equals 8 pi mu dt over dh. Sorry, wait, dh over dt. And so we will just add that up into our equation, which we said is 8 pi mu dh over dt. So now that we have this equation here, we are going to rewrite it in simpler terms, which I'm going to go all the way down here. And you arrive at the equation dh squared over dt squared plus that 8 pi mu, sorry, I forget the name of that one, over PAH dh dt plus your gravity times your height over your length equals 1 over rho L times P. And now we are going to actually rewrite this and label some of these. So we're going to label this beta. This term will be this, and this final term will be alpha. And so now we were able to break this down into a Laplace transform. And to do that, we set up the equation s squared times h plus beta sh plus r times h, and this is going to be set equal to alpha p. And then you can break that down even more into h terms, in which you get h equals alpha over s squared plus beta s plus this all times p. And then this portion here in the denominator is going to be our transfer function. All right, as you can see, I've moved into Colab. We're going to actually simulate this process, and I will walk you through what happens when we actually take it to a graph. So first, let's begin with that. I already have the libraries embedded, as you can see. And first, we're going to set our gravity equal to 9.8 meters per second squared. Heat our rho to be set equal to 1,000, and this is kilograms per meter cubed. And we need lambda. Sorry, length, not lambda. Length is 1 meter. Our mu, we're going to set equal to 1e to the negative third. Pi is going to be 3.14. Our diameter from the specs is 1 centimeter. Our area is going to be equal to pi times diameter squared divided by 4. And now we also need our alpha, beta, and gamma. Now we're going to set our alpha equal to 1 divided by rho times length. And again, all of these equations are from what we derived on the iPad before. Beta is equal to 8 times pi times mu divided by rho A. And then lastly, gamma is d divided by L. I don't know why I did colons here. Man, my brain is just in a fog. Okay, there we go. And our k value, we're going to set equal to alpha divided by gamma. Tau is going to be equal to 1 divided by np dot square root of gamma. And then zeta is going to be equal to beta divided by 2 times np dot square root of gamma. So now we will run this, and we are good to continue. And so now we just have a little bit of code left to do before we plot this. And so we're going to have GP is equal to K divided by tau times, squared. This will be multiplied by S squared plus, plus 2 times our zeta value times our tau value times S plus 1. Now we also need our time and our height, which is going to be equal to sim GP lam. I always forget how to spell lambda. LAMBDA. I think that's how you spell it. T colon 5e to the third. N is going to equal 1,000. And our dt is going to equal 0.1. Now we need to fig equals make underscore subplots. And fig dot add underscore scatter x equals t, y equals h. Let's run this. K is not defined. This should be lowercase. Something's a little wrong. I'll be right back. I'm going to try and fix this. It was a very easy fix. Thankfully, I accidentally had rows set to 100 instead of 1,000. So I fixed that, and as you can see here, as time goes on, you are creating more of a stable system. So at the beginning at t0, you have lots of these crazy oscillations, and then right around about just under 40, I'd say it's a completely stable system. So now we are going to go move back onto the iPad. So now we are back on the iPad, and we are going to start by writing down some equations. That first equation is going to be, let's get back here, K1 over tau s plus 1, not t, tau s plus 1. And then we're going to multiply that by the same thing, K2, not the same thing, similar, K2s plus 1. And we're also going to have this equation of GP, which is going to equal K all divided by T2, sorry, I keep writing T, it's tau. Tau 2s squared plus 2y s plus 1. And so now we're going to rewrite this equation in terms of tau, and you get GP is equal to K1, K2 over tau 1, tau 2 s squared, tau 1 plus tau 2 s plus 1. So now we want to kind of break this down even more, and we want to say that tau is equal to the square root of tau 1, tau 2, and then also tau 1 plus tau 2 is equal to 2 zeta. And when you rewrite this, you can say that tau 1 plus tau 2 over 2 squared is equal to square root of t1, t2 squared. So now we're just a few steps away from getting the actual equation that we're looking for. And so you're going to rewrite this as tau 1 squared plus 2 times tau 1 times tau 2 plus tau 2 squared, all divided by 4, is greater or equal to 4 tau 1 tau 2. I also misspoke here. There's no zeta there. I don't know why I put that there. And so then after rewriting this, you have tau 1 squared minus 2 tau 1 tau 2 plus tau 2 squared is greater than or equal to 0. So then finally, you have tau 1 minus tau 2 squared is greater than or equal to 0. And this is for a system of first order system, always dampered. And as I mentioned, we are now going to go back into Colab. All right, so as you can see, we're back in Colab, and I'm going to begin coding out this simulation. The first thing we want to do is label K, which is going to be 1. We also need tau, which is going to be 1. And then, no, no. And then zeta, which is going to be equal to 0.2. Next line of code, we need our Wn value to be equal to 1 divided by tau. This is just our natural frequency. And then the final thing will be our GP value, which is going to be K divided by tau squared times S squared plus 2 divided by zeta times tau times S plus 1. Then we need our time and our height values. And those are going to be a sim of GP. As you can tell, this is very similar to what we coded in the last part. T colon NP dot sin WN times T. And then we have N equals 1,000 and DT equals 0.1. Again, we need to plot this. Fig equals make underscore subplots. And then fig dot add underscore scatter. And that will be the x-axis is going to be equal to time. The y is going to be height. And the mode is going to be equal to lines. Run it. Something seems a little off. Let me fix this. So you would have figured out what was wrong. I accidentally had 2 divided by zeta here instead of 2 times. So when you run all of that, you have these oscillations, and you're actually able to adjust these, how far the waves are apart. You can multiply this by 0.5, and you will see that they become much further away, and as you get smaller and smaller, they'll become much farther and farther away. And technically it's at 1 right now, so you can see if we did 2 times this, they would be even closer than original. It could become super tight and actually also extremely unstable at the beginning. So as you can see, we have created our simulation for this problem, homework 4 part A. Thank you for watching. I hope you enjoyed.